Okay, everybody see this? All right. So hi, we're team Everything is Awesome, Rami and myself. There we go.
Explain the team's origin, please. Just kidding.
So in the beginning, we got some Legos, bought a bunch of stuff, started assembling it into a platform, and then this is the platform actually running. So this is our robot assembly. So that's one of our motors and part of our motor system. Then we were calibrating it very scientifically of seeing how fast the thing can go. And so we calibrated it well. Then we're also, so the other part of the robot is a sensor module. This is the elevator that goes up and down. And in the background there, you can see this is the sensor with the camera and the depth, with the RGB camera on it and the depth camera on it. So, and that's what the robot looks like combined. We did a bunch of debugging. This is an example of debugging the depth sensor. There's interest, like you can see different depth resolution versus RGB resolution. So every dark point is an RGB point, and the depth sensors were like more pixelated squares. Some of the lessons learned. Early on, we were trying to remind each other not to eat the data set. Since some of it was edible and it was in the kitchen, so we just finally separated out of the rest of the food that we planned on eating. Another lesson learned was it was really great. I think everybody was mentioning this, building something with Monty end to end, so that we had to write and understand every single part of the Monty system. Like I know Rami and I are way more familiar with how the whole system works now. Of course, quaternions. I understood quaternions for a little bit, so that was great, and I think I still remember them. There's a resource that really helped with the intuition. Some of the Monty framework things. There's some ideas for action refactors that I want to do after we're done. Noticing too many resets happening before an episode. Like, if you're running a simulation, you never notice it. But if you have a robot, it's like, why is it doing the resets so many times before it starts? So that was a neat finding.
Yeah, we ran into the same problem, spent way too much time on it, and then decided that we'll just always have to press the button twice before we start the experiment.
We had to do the same. Like we had to take two pictures, and because the first picture would always be black for whatever reason.
Nice.
Yeah.
I removed the extra reset, so that was my. Because our coding approach was we just forked the entire Monty repository and we just hacked whatever we needed to. So that was convenient. That was also a convenient approach to the hackathon for us.
Yeah.
Picking coordinates that make the problem easy. As you saw, our robot has a central platform that rotates and a thing that goes up and down. So we're like, our units are the robot radius and we are on the unit circle. And that simplified a lot of things immediately. So that was super helpful. Next on debugging and visualizations.
Yeah, I think to me, I feel like having a very good, this is what I figured out early on, that if you have very good visualizations and a debugging, that will go a long way in something like this. So yeah, we started working on some nice visualizations. You'll see that in the next few slides, but basically we're able to see the sensors positions live as it's basically making movements, and basically also what the current MLH is, or what Monty thinks is happening and what the rotations are and all of that stuff. We had some trouble with the coordinate systems, so we started using, so for the get state of the agent, so that we know where the agent is, we're using a different coordinate system that was in Monty, and we figured it will still work fine. But then it does not plug well with the depth to 3D, so we ended up changing all of our computations for the get state of the agent, and that's where learning the quaternions also. That's where we started looking into quaternions too. And then we tried to do model scaling. So basically, we're using different like a different scale than what is in the data set that was provided to us before. So that did not work very well, and I'm not really sure why. But so we added some code into the grid object model that will basically, you can just say scale this model by this scale factor, and it will just scale the mesh and recalculate the KD tree and everything. But that still did not help very well. So what we ended up doing is that we basically trained our models, but then the models that we trained are very sparse, so they may not work very well. But the idea is that if we train a dense model, it will work better. But you'll see that we still have some performance, kind of reasonable performance. And early on, like in the first day, we had a lot of networking issues, and it basically, the reason is they have multiple sources of, like they have multiple routers, and if you have the different clients are connected to different routers, they will not be able to talk to each other. So what we ended up doing is that we needed a router, but then we could not make that router connect to the internet except through like a hacky solution where we plug it into a Wi-Fi extender, and that Wi-Fi extender gives the internet to the router, and then we can connect to the router. So, but the cool thing about what we built is that we could actually like decouple the simulator from Monty itself. So what we tried is running 2 different Montys on the same hardware. So basically, Tristan and I, we were running experiments at the same time, and we were fighting for the hardware, which was very cool to see basically like the sensors moving. Like I give it a command to move somewhere, and then Tristan just moves it somewhere else, and then we start arguing about, needing the resources and all of that. Yeah, and a lot more stuff that we, the depth camera was like giving us a lot of trouble. So yeah, too much troubleshooting and debugging that went there. And yeah, like I said, a debugging setup goes a long way. Yeah.
Okay. So we did with troubles with changing the scale of the existing data set, we ended up training on the data set ourselves. So if you don't recognize it, but that is a cup. All right, and
yeah,
so this is training sped up 40 times. So on the left, you see the visualization being built, and on the right, you see the robot using our training policy was essentially orbit around the object from the bottom up and just kind of scan it. And so that's the idea behind that. This is what the final scan for like the cup looked like. So it does end up looking kind of like a cup.
It looks like a cup, but the handle is,
yeah.
I think we have some trouble with the depth information and maybe the focal point of the, like the field of view and all of that stuff. So it's a perfect circle and everything, but like the handle is a little detached from the cup. And this is why our evaluation works fine with the trained models, but then maybe this is why scaling the meshes didn't work very well, because they're kind of different. During inference, we can see that so this is a different kind of visualization where it's basically I'm plotting the current MLH in real time. So it's basically if you can figure out the rotation, the rotation, this little dot is a sensor. Basically, this is where it thinks the sensor is compared to where the mug is, and it was able to figure out that the cup was right side up, but it could not figure out the rotation, like basically the rotation on the y-axis or like where the handle is. So, but it could separate it from all the other objects in the data set. So that's also good.
Yeah. And essentially we used based policy, just random actions. We had to kind of rewrite it a little bit to use our actions, but as you can see in the video, those actions are just purely random. The up, down, and rotating around the object.
But the sensor's always guaranteed to be on the object in these cases?
No.
How do you move back?
It's random.
It's built in?
Yeah. So if you're off object,
how does it know that it's off object, I guess is my question.
Well, there's the transform, right? So based on the depth, it knows that the depth is...
Yeah, so if the depth is like too far, then you're not an object. Okay. So we go through the building the semantic labels based on the depth.
Okay. I have more questions
Okay.
we can get into.
Is this the time for live demo, or do they come after all the presentations?
Maybe we wait until after the presentations and we pick one object that we all demo on.
Okay, sounds good. That's it.
Nice, great job. Looks really cool.
So can I ask those same two questions with regards to,
Yeah. Could you ask them again?
yeah, I gotta bring them up. Okay, how did your project demonstrate Monty's capabilities, and how do you see Monty with the application you're doing for the future?
Yeah, so demonstrating Monty's capabilities, I think this would count as probably, I don't know, I'm not sure, but this is probably the first system that has actual movements in the world, basically, instead of like saccading over an image. So it's not like we're taking an image and then we're moving a patch over the image. It's actually the patch itself is moving through the world, which is, in my opinion, is very different from what we had before. So it's demonstrating a different side of Monty's capabilities with an actual motor, basically, so that this thing works as a sensory motor.
Okay, yeah, can I throw in there? So, like, just one point about the patch. Like in the previous presentations, you saw like a full image of every, like being taken. Literally, Monty only sees those dots. Like, there's nothing else. There's no image of the cup. There's nothing. Monty learns just those dots on the left. And based on that, it learns to recognize objects. There's no full picture given to Monty at any point. Good.
Yeah. And then in terms of future capabilities, I think that so this is a first step. In my opinion, there's just like with the drone team as well, there would be opportunities there to explore voting, which I think is very important. It's easy now. We're building this with Lego, so it's easy. Like we could add a different sensor and that's a different angle, and then we can just move it. We can move it independently, or we can move them together as part of one agent, so they can move like like two sensor patches on a finger together, or they can move as like different hands, and then they like look at different parts of the mug. And so basically, it's very extendable the way that we set it up. So yeah, if that answers your question, I'm not sure.
Yeah, I think it's a great point. Like, it's the very first time that Monty is working with a motor in the real world. It's a huge thing. And then I guess just for us, it will be a great setup to have to test Monty in the real world. Right now, we basically everything that's a bit more complex, anything that involves movement, we have to test in simulation. So now we have a test bed in the real world, and we could give it any kind of object. We don't have to create like a simulated object data set or anything. We can pick something from the kitchen and put it on the platform, see what Monty does.
Yeah. It also scans very nicely. It scans very fast, but then it's still kind of sparse compared to what I would expect. Like I looked at the meshes that you gave us, and they're very nice, but like very dense. So this is like sparse, but the fact that it still works even with those sparse models is mind-blowing to me. So
Does it work at any speed? I mean, if you slow down the motor or speed it up, does it still have the same results?
Well, slowing it down is always easier. Speeding it up, we're running at a kind of a high speed actually, and but we're limited by how much time it takes to transfer the image from like wirelessly from the sensors to the computer and process them. This is actually the bottleneck. One of the challenges was I was sending a bigger, so that to be able to stitch the depth camera with the RGB, I was sending both like bigger images from the Raspberry Pis or from Monty, from the robot to the computer, and then stitching those. but then we found out that if we just send the patches and do the computations for which patch we want, if we just basically send smaller images across the network, it goes much faster. So Monty doesn't have a problem. Actually, Monty is much faster than the bottleneck of sending images to the network. So yeah, it works. It works fine with high speeds, I guess, short answer.
And yeah, to Monty, it doesn't matter how fast you move or in what pattern you move over the object. It's not like you need to have seen that pattern before during training. You can generalize to any like speed of movement as long as, like what Rami says, the transfer is fast enough.
Yeah, and you can increase.
You're
You're
muted.
muted.
And you can speed up the inference by having Monty have multiple sensors. So I have like 1,000 sensors looking at something. You can recognize it instantaneously rather than having to move, or you can move it once. So yeah, you can. Once we put this in hardware, this could go very, very fast.
And another thing about the future, demonstrating future capabilities, as we have zero precise movement. So when the elevator goes up, we ask it to go a certain distance, but it goes whatever distance it manages. Like there's minimal distance. When it rotates, we're like, rotate by 7 degrees. It's gonna do whatever it wants. So, but as a result, we were able to work on proprioception and make sure that Monty was still processing where the thing actually was. So there's no, so what we also demonstrating is you don't need any sort of precise movement as long as you figure out where you end up. And the policies still seem to work okay and still infer and train objects, even with imprecise motor control, which is a new demonstration outside of simulation.
Yeah, actually, there were some times where the rotation robot, that one that rotates the platform, it was not even moving. Like it tries to move, but it looks like it doesn't have enough power, or like we're just doing small steps. But basically, because we're using proprietary, we're getting the position of the agent, it doesn't matter. So basically, we'll just add points at that same location, or depending on how the object is built, it doesn't need to add these points. So the lesson learned is that just being able to get an accurate position of the agent is more important than moving the agent somewhere, or trying to move it to somewhere accurately. It doesn't matter as long as you're able to get the position accurately. So that was helpful.
Yeah, awesome. Looks great.
That's how they got their name.
Yeah, everything's awesome.
That was Tristan's idea.
What you're observing now is it's resetting into the starting position.
Cool.
Okay.
Oh, wow, already hot sauce, most likely hypothesis. It's impressive.
I also think that might be Monty's heart, so I don't know.
Oh,
Oh,
oh, it's neck and neck.
yeah.
And you
Okay,
can
hot sauce back.
Yeah.
Neck and neck with what? I can't see that.
No, now hot sauce is a clear lead, but there was Monty's heart as well there for a few steps.
Monty's what?
Oh,
The-
detected hot sauce.
Oh, wow, good job. That's pretty
Nice,
awesome.
nice.
Wow.
let me share my entire screen actually, because that will be better. So pick another one.
Can you do the mug?
Yeah.
They already did the mug. Let's do something different.
Okay.
Spam.
There
We
it
could
is.
do the bug and something.
Yeah, do this. You can
ours
do
are-
the spam.
Ours are pretty quick. Hold on, let me just turn off I wanted to share because I wanted also you see. There we go. All right. What's on the? Okay.
Yeah, it's so beautiful.
All right, here we go. Again, it's resetting.
Oh, Terry, by the way, the spam can here is called potted meat can.
Oh,
the-
really?
Full name in the data set.
Oh, okay.
No product placement.
And by the way, you can see the models in the upper right corner of the visualization. Like that's all that Monty knows.
That's cool.
Very sparse. Interesting that it was sparse images.
Okay, I mean, it's between the two, limited mug or potted meat can.
What's the back end for the visualizer?
You keep saying global matching step 33.
Oh, we didn't debug those logs.
Maybe it's Maybe
What's happening
upper
is
goal
the
state.
camera is above the object, so it wasn't getting any
Ah.
sensor input, so it was just bypassing the learning module.
Of
Okay.
object.
Oh, nice. There you go.
Whoa.
Boom.
And- Wow.
What else you want to identify?
How about the Numenta brain?
All right, this one is a little different setup. You have the platform.
I don't think this one works very well.
Do you have the platform? Okay. Yeah, it needs the top platform, right?
I don't remember.
Yeah, just put it on top platform. So we have an extra platform for this one because our sensor didn't go far enough to see it on the platform that we built. So and we
Yeah,
also
and presumably the platform is kind of part of the model.
yeah, although like we're not sure if this is the platform we used or if we used a different one. So we'll find.
Okay, cool.
So
Testing robustness.
yeah, so here you go.
This object is also very small that the patch is sometimes just off the object a lot, and that's somewhat it doesn't work for that reason.
And hopefully it will not fling the brain off of the platform either. It's pretty light. We don't have many tolerances built in here.
A flying brain.
Yeah.
Oh, don't see Monty's brain in the hypothesis space.
Yeah. This one might not work. We'll see. Yeah, right now the sensor is above. So when you're seeing stuff like this, it's just not getting any data because again, our policy is just purely random movements.
Also, the time flight sensor works best with shiny objects and objects that are not like metallic or whatever. They don't really give good data.
Oh yeah, sorry. Visualization.
Yeah, it thinks it's a tuna soup can. This is why it's plotting the tuna soup can graph.
Wait, tomato soup or tuna can? Tomato soup.
Sorry, tomato soup.
Probably,
Yeah,
think
I
it's
guess
the
that. So,
platform, probably. Okay,
but you know, you got an example of a failure mode.
That's
if-
not bad for free.
Yeah.
Do we
Yeah,
get a
that's awesome.
second try on the spam can?
Yeah, what if we get the brain? No.
It's actually pretty good about the brain. You just put it on the bottom, right? Yeah, just normally. Yeah,
Or
I
the
mean,
heart?
The heart.
the heart, sorry. Yeah. So it's pretty good recognizing Monty's heart. Then you can see the image of that's its model of the heart.
Yeah, wow.
That's pretty cool. Yeah, do you want to try the spam can again?
Yeah, should we try one more? Just
Just to
you change
hopefully
the
have this
config back?
success. Yeah,
Okay. The checklist.
yeah. I would say the prize for highest accuracy definitely goes to you guys, but want to have a little bit of success.
Sounds good.
So-
Yeah, I'll stop sharing as soon as this completes.
So are you like in Monty when you rotate? Is it moving the agent around the circle?
Yes, it's we are faking it orbiting an object. There we go. Monty's heart.
Monty's heart.